'Cause you need to get back in the arms of a good friend. And I need to get back in the arms of a girlfriend. I didn't know nobody, and then I saw you coming my way. I didn't know nobody, and then I saw you coming my way. Don't you need to get back in the arms of a good friend? Oh, 'cause honey, believe me, I'd sure love to call you my girlfriend. Don't you need to get back in the arms of a good friend? Oh, 'cause honey, believe me, I'd sure love to call you my girlfriend. 'Cause you got a good thing going, baby. You only need somebody to love. Well, you got a good thing going. You're only looking for someone to love. 'Cause you need to get back in the arms of a good friend.
All right, so today we're going to start on the last module for this course, trees and tree-based data structures. Basically data structures, like we've already seen, stacks and queues, those enforce a structure based on their interface, that you can only work from one end or the other end or both ends, right? But data structures are good because the structure can be exploited for efficient operations, right? Our motivation is that we want our data structure to support the four basic CRUD operations: retrieval and search, insertion and deletion, and we want them all to be efficient. That's the key word there, right? And we haven't found that ideal data structure that offers efficiency with respect to all four of these operations. We'll get close, but we won't get there entirely. But let's review linked lists, right? With linked lists, they had efficient insertion operations, but only if you worked at the tail or the head, right? Those would end up being constant time algorithms because it's just creation of a node and then the exchange of a couple of references. And so those were efficient. But on the other hand, you paid for that efficiency because if you wanted to do arbitrary insertion or index-based retrieval, it would be necessarily order n. If you wanted to get to that middle element, you'd have to start at the tail, or you'd have to start at the head, and you'd have to traverse to that index, right? We also looked at array-based lists, and there it was just switched. That an arbitrary index-based search is going to be a constant time operation because of random access. You know the memory address where your array starts. You know how many bytes each element takes. It's all contiguous. You can immediately jump to that memory location. If it's sorted, we can also exploit that because it's going to be binary search order log n, right? Sorting is a structure, basically, but it's a structure based on the state, not the behavior. Insertion, however, came at a big cost. If you wanted to insert something at the beginning of an array-based list, you had to shift everything down and then to make room for it, right? Because you wanted to make sure that everything was contiguous. Then we looked at stacks, queues, and decks, right? All the operations were always efficient, right? But we were cheating, right? This was only because they were restricted access data structures. Restricted access data structures, right? We restricted how you could use them, and we didn't allow you to do these arbitrary things that were inefficient. We only allowed you to do the things that were efficient, right? And again, all of the operations are going to be order 1, but we cannot do arbitrary CRUD. So that's not going to meet our standard either. We want to. Our ultimate goal is to have an efficient operation for a general purpose collection data structure, right? Trees provide a potential for those efficient operations. We're not going to get there fully, and you do that in, say, Computer Science 3, but we're going to get almost there, and we're going to realize why we can get there, right? All right, so what are trees? Well, first of all, we need to define graphs, right? A graph is a collection of nodes, sometimes called vertices, and edges that connect those nodes. Some nomenclature here, we call them nodes in computer science because they're not just vertices, they actually hold things, hold our data, right? In pure math or pure graph theory, they're just going to call them vertices, right? Generally, we use n to denote the number of vertices, right? In fact, let me add another thing here. Since have you gotten to graph theory at all in 235? Not yet. All right. Well, then formally a graph is a tuple, VG, right? Where V is the vertex set, and E is the edge set, right? A set of pairs, right? And those are generally tuples or subsets, unordered subsets. Depends on what kind of graph you have. But generally, we use n to denote the number of vertices. In other words, the cardinality of V is going to be n. Okay. We generally use m to denote the number of edges. So, for example, the cardinality of E will then be m. Okay. For us, edges are going to be undirected, right? If I'm connecting a node A to B, that's the same thing as connecting a node B to A, right? That's an undirected graph. So if I were to draw a graph over here on the side with a bunch of vertices, let's go with black there, right? There's a vertex, 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 right? And if I label them A, B, C, and D, right? Then here's one graph. Here's a connected graph, right? Then CD is in the edge set. Let me go ahead and move over there entirely now, right? And then CD is actually equal to DC, right? And if you're looking at this from the perspective of the graph, if you want to traverse the graph, if you start at C, you can go to D. Well, you can also go back, right? You can go back and forth. There are things called directed graphs where these have orientation, right? And if you have an orientation, you can't necessarily, it's a one-way thing. You can go from C to D, but you cannot go necessarily from D to C. But because these are going to be undirected in this class, A to B, B to A, doesn't matter, okay? What's the maximum number of edges with n nodes in it, right? So the maximum number of edges in a graph with n nodes is ... Let's do some combinatorics, right? So let's look at some examples first of all. So what if I had a graph where there's just one edge? What's the maximum number of, or just one vertex, excuse me. How many edges can you draw with just one? Now careful here, there are things called, this is called a pseudo graph, I think, where you can have self edges. They can be directed or undirected. And you do want that sometimes with stochastic processes because you're basically going from one state to another state probabilistically. So with probability, say 0.2, I go from A to B. With probability 0.1, I go from A to C, right? Well, there's also a probability that I just stay at A. And so you can have self-loops, but those are pseudographs, and we're not going to consider those, right? I can't draw any edges there, 0. What if I had 2 vertices, A and B? What is the maximum number of edges that I could draw? 1, because you choose 2. Here's the key word here. You choose 2 of those edges to draw between them. What if I have 3? 1, 2, 3. Now what's m going to be? The maximum number of edges. 3, because I can go 1, 2, and 3. All right? Just one more here, and then we'll generalize this. 1, 2, 3, 4. Right? Equals what? Well, I can go between those 2. I can go between those 2, those 2, those 2. Is that it? I can go between those 2, and I can go between those 2. How many did I draw? 6. Right? Generally, what would you do? If you had all these edges, right? There's a whole big graph over here, right? Well, isolate 2 of them and draw an edge, right? So if I have n vertices, then I choose 2 of them to draw an edge. How many possibilities are there then? We write n choose 2. Right? Have you seen this before? Or you might have seen it instead on your calculator, C2n or CN2, right? Something like that. This is the proper way of writing it, though. Right? And if you want to expand this out, what is it going to be? It's going to look very familiar. It's almost exactly Gauss's formula, right? Basically, you can derive this if you really want to, but otherwise, there's our answer. Right? In other words, it's going to be order n squared. Right? So m is going to be less than or equal to is less than or equal to n. Oh, if you want, I'll put it in the notes here. How do you do choose? N choose 2. There we go. That's how you would end up writing it. And by the way, the LaTeX for doing that, you can see it when it's posted, but the LaTeX for doing that is going to be this, right? And choose 2. Right? Okay. A tree, however, is not a full. We're putting restrictions on it because again, what we're trying to do is we're kind of trying to come up with a data structure. A graph is unstructured, right? I mean, there's a structure in it. But we call that a topology, how it's shaped, how it's connected. Right? There's no actual rules on it. You can connect whatever you want, however you want, right? Or not connect things, right? But what we want is a more structure that we can exploit. So a tree is going to have to be a connected acyclic graph with no cycles, a graph with no cycles, right? So what does connected mean? Connected means there are, from any vertex or node, you can get to any other vertex or node through some, and we'll define this later, some path, right? What does acyclic mean? I already defined it, click, right? There are no cycles, right? That is paths that start and end at the same vertex or the same node, right? Let's just look over here at a really quick example. In fact, I'm going to bring in a nice looking example from somewhere. Let's go ahead and go with iCloud. There we go. And where's trees? Trees. And I want a graph. I just want a regular old graph. There we go. There's a graph. Right? Is this a tree? Definitely not. Right? There are cycles. Give me one cycle. I can go from any vertex. I can start at any vertex. Let's say A here. Right? So let's start at A. Now let's take a walk around by taking edge to edge to edge. And then returning back to A. One such path would be going to D, then over to F, then over to A again. There's a path, and we call that a path of length 3, because I went 1, 2, 3 edges to get there. But I begin and I end at the same vertex. Right? There are other paths, of course. You can go from A to E to G to C to D back to A. How big of a path would that be? 1, 2, 3, 4, 5. Yep, a length 5. Okay. It's connected means that I don't have the following situation. Here's A going to B, going to C. Here's D, and here's E going to G. There we go. There is a disconnect between this graph, right? I've got one component over here that's connected. From any vertex, I can get to any other vertex, but I can't get to any vertex over here because it's been disconnected. Right? It's kind of like a network, right? You can, A can talk to B, B can talk to C, C can talk back to B, and likewise A can talk to C through B, but it can never talk to D over here. Everybody over here can talk, but you can't talk between these two things. This is disconnected. Right? What we're only going to consider are connected graphs. Right? So otherwise you would have data where you start at one location and you can't get to that other data over there. That's kind of useless. Right? So some more definitions and terminology here. A path in a graph is a sequence of connected vertices. Right? So you can go from A to B to C. Right? The length of a path is the number of edges on it, right? Which is equal to the number of vertices on it minus 1. Minus 1. Okay, that looks kind of ugly. Let's go ahead and LaTeXify it. There we go. Minus 1. Why is that? Let's go over here and look at this again. Give me a path in this graph. Let's go ahead and erase this, right? Okay. I can go from, say, A to D to F over to B. A to D to F, or I can't go to B. Let's go to E instead. All right, there we go. All right. Now, that is a path. The path is length 3. How many vertices are on it? Vertices is 4, right? So it's always minus 1. Why? Because if you look at your fingers, how many gaps do you have between the fingers, right? If you have 1, 2, 3, 4 things here, then there are necessarily 3 things between them, okay? So that's the length, and it always involves that number of vertices there. We're going to keep things simple, right? We will only consider what are called simple paths and eventually simple cycles. Those are the paths that do not traverse edges more than once. Right? You can, and by implication, it doesn't traverse any edges, any vertices more than once. For example, here is another path, and this is a legal path. Right? I can go from A to D to F, back to D, back to F, back to D, back to F, and then finally on to E. Right? That is a path. Right? It's me just going from A to D over to F and back and back and back and forth a bunch of times, right, until I get over to E. That is not a simple path. Generally what you want in graph theory is you want the shortest distance. You don't want to needlessly be going back and forth between 2 points because you're wasting your time. So we're not going to consider those. We're only going to consider simple paths. And likewise, simple cycles. So a cycle is a path that begins and ends at the same node. And the length of a cycle is going to be the number of nodes on it, which is equal, in this case, to the number of vertices on it, not minus 1, right? Because you will eventually come back to the original location, and that's one more edge, right? So if I've got a cycle of length 3, that means that I've got edges 1, 2, and 3. I've also got nodes 1, 2, and 3, right? All right? It also has to be connected. By the way, a disconnected tree or a disconnected tree is called a forest, right? We're not going to consider those. Right? All right, so let's make some observations about trees and why they have structure. In a tree with n nodes, there are exactly n minus 1 edges. Let me prove it to you. All right, come on over here. Now, is this a tree? No, we've already said that it has cycles. It has many cycles. So let's start getting rid of those cycles. Come on, I just want white. There we go. Let's start trimming this tree. Let's get rid of some edges here to get rid of cycles. Right? Well, we already said that A to D to F. Well, that's a cycle. So let's go ahead and get rid of that Right? Now that's no longer a cycle. A to D to F, right? That's not a cycle. But are there cycles still? Yep. Okay. Give me another one that I have to get rid of. There are lots of choices. Right? I could get rid of that one. Why? Because there was a cycle between, oops, sorry. Do I need to get rid of that one? Yeah, there was a cycle there. Okay, that got rid of a cycle. All you have to do is identify a cycle, usually triangles, and get rid of those edges, and you'll be good. Okay? Let's go ahead and get rid of F to E because there's a cycle of length 4. 1, 2, 3, 4. Right. We still have cycles. 1, 2, 3, 4. Let's go ahead and get rid of that one. All right. We still have a cycle. B to G to E. Right? There we go. So let's go ahead and get rid of one of those. And let's go ahead and get rid of that one. Are we good to go? Nope, there's one more. What? 1, 2, 3. All right, so let's go ahead and get rid of that one. Now are we good to go? Yep, there are no cycles. Do not misinterpret this thing as a cycle, right? This is not an intersection point, okay? Take this and move it over here. Or actually, take this and move it right here, right? And there's your connection, and it's clear that there's no crossing edges, right? All right, let's make some observations now. How many vertices do I have here? 1, 2, 3, 4, 5, 6, 7. Right? Now that this is a tree, and by the way, it's not. It is still connected. If I did one more, right, that would isolate C. It's an isolated vertex. We don't want that. We want a connected graph, a connected tree. So how many edges are there? 6. Right. So posit a theorem here, right? So we already wrote it out, I guess. With n nodes, there are exactly n minus 1 edges, right? 7 and 6. Why is that true? I demonstrated that with an example, but that's not a proof. Right? Suppose that we had n vertices here, 1, 2, 3, 4, whatever, right? And it was connected, so we've got a tree here of some sort. Right, there we go. We've got n minus 1 edges. Could it have more? Add one more edge. What do you end up doing? You end up inducing a cycle, right? You could actually. We're not going to prove this, but you could prove this using the pigeonhole principle, etc. There are some other counterexamples, though. Of course, you could have this, all right? 1, 2, 3, 4, right? So there are four vertices here. How many edges are there, though? 2. But guess what? It's disconnected. It's a forest, right? So in a connected acyclic graph, you have exactly n minus 1 edges, right? Because the removal of any one edge will disconnect it, right? So you can't go lower, right? It'll create a forest. You cannot add any because it will induce a cycle, right? So what structure does this give us? That the edge set is going to be order n, right? It's linear. Before, what did we say it could be? It could be quadratic. Already we've given ourselves some structure, right? Trees are basically small graphs, or sparse graphs, the opposite of dense graphs, right? And another observation here. In a tree, the number of paths between any two vertices is exactly 1, right? There's exactly one path between any two pairs of nodes, right? What if that were not true? What if I could go from A to B through one path here, call it P1, and then there was a completely separate path over here, P2, that I could get back from B to A? Well, guess what you just created? A cycle. Because it's acyclic, we have this condition right here. That's a lot of structure already. Right? Let's give it some more structure. Right? All right, first of all, natural trees. I tried to draw a happy little tree over here originally, right? Real trees in real life, how do they grow? They grow up, right? Down here at the bottom, you have things called roots. Up here at the top, you have things called leaves. Our structure is going to be different. Our structure is going to grow downwards, right? And this goes back 150 years to Cayley, a mathematician named Cayley. Have you ever heard of Cayley before? Cayley's theorem or Cayley's Cayley graphs or anything like that? All right, you'll eventually hear them. Cayley algebra, Cayley tables, right? Trees can be oriented top to bottom and left to right, right? The top is a single node called a root. Now, before we do this, actually, let me go ahead and come over here and let me give you another graph, but that's actually a tree, right? Where's my tree? There we go. There's an unoriented tree, right? So that's the same graph as before, but I erased different edges, right? There's 1, 2, 3, 4, 5, 6 vertices, and there's 1, 2, 3, 4, 5. Did I count them right? 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go. And 1, 2, 3, 4, 5, 6 vertices, right? Now, what I want you to do is imagine that I've got an even better tool than GoodNotes here, and I want you to grab any node. Let's say D here, right? Let's go ahead and grab D, pull it out into the real world, and then dangle it, right? And then let gravity take over. What would it look like then? D here would be at the top. It would be connected to A immediately downward. A is connected to E and F. There we go. E is not connected to anything else below it, right? F is connected to C, and C is connected to G, and G is connected to B. So if you took it out and dangled it by D, you would get a structure that looks like this. Right? Now, it doesn't have to be a D. It could be something else. Give me a vertex. Choose your favorite vertex up there. F? Okay. Let's dangle it by F here. Off of F is hanging A and what? C? Right? Off of A is hanging D and E. Right? Off of C is hanging what? G and then B. Right? There. Now, we call this a topology. The topology is the same. We didn't actually change what is connected to what in this graph. We just changed the orientation. We put a different vertex at the top, and then we let gravity take over. Right? So there's how you can visualize it. Right? At the very top, you have a single node called a root. Right? The roots are at the top. The leaves are going to end up being at the bottom. Right? Nodes under a node are called children. It's kind of like a family tree now. Right? Then family trees also grow downwards because up here you have your ancestors. Down here are the descendants, right? And you're in the middle somewhere if you have children. Right? The node above it is called its parent. Right? Any node with 0 children at the bottom, you haven't had any children yet. You're called a leaf. Right? Okay. So let's go ahead and look at another orientation here and start labeling things. File. Where's my oriented tree? Okay, fine. We'll do it from this one. Let's go ahead and get rid of this one. This one's a little bit more interesting anyway. All right. All right, so let's start labeling things. The root in this case is going to be F. F has 2 children. A and C are F's children. D and E are A's children. And by the way, you can go grandparent and grandchild. So F is the grandparent of D. D is the grandchild of F because you're going downwards in a family tree, right? D and E sometimes are called siblings because they have the same parent. You can call these cousins over here, right? Just like you would in a family tree. What are the leaves, though? What are the nodes with no children? D, E, and B. That is B right there. Right? G has a parent and a child. What is the only node, by the way, with no parent? The root. Yep. Always going to be the root. Okay. All right. So there's our terminology. And again, you can call these parents, children, ancestors, descendants, grandchildren, grandparents, cousins, whatever you want to call it. Right? We're going to put in even more structure now. We're going to say you can't just have as many children as you want. You can have at most 2 children. You can have no children. You can have 1 child, or you could have 2 children. Right? And we're going to orient it left to right as well. When you have children, you have a left child and or a right child. It's oriented left to the right. Right? So there are possibilities. You can have you can have neither. You can have a left child, no right child. That's what I'm saying there, no right child. You can have a right child, no left child. Right? Or you could have both a left child and a right child. Right? This is what's known as a binary tree. Right? And it's binary because there are at most 2 children. If you change this definition and allowed 3 children, up to 3 children, you would have what's called a ternary tree, quaternary tree, quintenary tree. I don't even know if that's a word or not. I don't know. If you allowed it to have up to B, you would have what are called B trees, right? Where B can be set to 10 or 15 or 20. Right? And now you have the makings of what's called a database. Databases use B trees. Right? More terminology. Right? So the depth of a node, right, of a node U is the length of the unique path from the root to the U. Remember, we said that it was unique already. That was one structure that we observed over here. There's exactly one and only one path between any 2 nodes. So if you consider the node U and you go back up to the root, that is the depth of the tree. Let me show you a larger tree. There we go. Where's our, let's go with that one. All right. So first of all, verify that this is a binary tree. Is there any node with more than 2 children? Nope. Right. D has 2 children. B has 2 children. But things like E, they have no left child, but they have a right child. Right. I has a left child, but no right child. And then R is a leaf. Right. So once again, let's label these things. The root is going to be A. Okay. In fact, let's look at let's look at all the nodes. Node. Let's calculate its depth, and then let's also any other notes here. And A, we've already said that that's the root. Okay. What about B here? B is not. It's not a root because we've already seen that there's another root. But is it a leaf? Nope. So it's what's called an internal node. All right. What is its depth? If I go back up to the root here, there's only one path, and the length of that path is 1. Likewise, C has a path of 1, and it's also an internal node here. Right. What about D, E, and F? What are its depths? What are their depths? 2, 2, and 2. And none of them are leaf nodes. Right? All right, well, before we go on down deeper, let's come back up to A. What is the depth of a root? 0, because what is the length of the unique path from itself to itself? 0, right? And again, we have pseudo graphs here where there's an explicit edge, but we don't do that here. In fact, you've probably done that in 235 already, right? Have you expressed things, post sets in terms of what's called a Hasse diagram, right? Hasse, right? A Hasse diagram where you've got these things and everything is reflexive, so you have self loops, but because it's a post set, it's implicit and you don't actually write those things, right? Instead, you write it as a Hasse diagram, top to bottom, right? What about G, H, I, J, and K? They all have depth 3, and none of them are leaf nodes. Right? Nope. K is a leaf node. Right? Yeah. And then L, M, N, O, P, Q. They all have depth 4. R has depth 5. Right? And then which ones are the leaf nodes? Let me go ahead and highlight those. Come on. It's going to be K, everything except M, you said? Yep, I agree. Right? Those are all leaf nodes. And they're in green because they're leaves. Right? Okay, good. So there, and by the way, we draw graphs like this nicely because of that layering right there. This is a level. This is level 1, level 2, 3, 4, and 5, and 6. And when we use the term level, right, it's going to be off by 1 from the depth. All right. Again, the depth of a root node is 0 by convention. The depth of the tree itself is the maximal depth of any node. So you can talk about a tree having depth as well. Come on. What is the depth of this tree? What is T? Here's my tree T. T's depth. It's going to be the deepest node. The deepest node here is R. And its depth is 5. So the depth of the tree overall is going to be 5. Basically, that gives you the maximum depth on it. Okay? All right. So, we'll come back to the Java demo here. Instead, what I want to do is motivate you today with some more math. Right? How can we exploit this structure now that we've built it? Right? All right. So, suppose that we had a full binary tree. Every node is present at every level up until the maximum depth of the tree. Right? If we can develop a way to insert, retrieve, and update elements, delete elements, etc., from a binary tree, such that all operations are proportional to the depth, and we can guarantee that the depth is small, say logarithmic, then we've achieved our goal. Right? Why? Everything is going to be proportional to the depth, and I've already said that the depth is bounded by a log n. Therefore, you can insert things, you can retrieve things, you can delete things, all proportional to log n. That's as good as binary search, right? Which was why we call these binary search trees eventually, right? Okay. Let me justify that with the rest of our time today, though. Right? All right. Why is the depth logarithmic? Again, let's consider a full tree. Let me give myself some more room here. Right? So at the level, or let's call it depth, at depth 0, and it's full, how many nodes do we have? 1. If I go down to the next level, there's depth 1, and I have 2 nodes. If both of the children are present, in other words, it's a full binary tree here, at level 2, we have 4 nodes. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 nodes at depth 3. ... Let's go up to the maximum depth D here. Right, ... How many nodes am I going to have down here? 2 to the D. Right? Following this pattern right here. Right? This is 2 to the first. This is 2 to the second. This is 2 to the third. So this should be 2 to the D. Now let's sum them all up. Right? So here's the math. If I sum up, say, K running from 0 up to D of 2 to the K. Let's keep it at I. You're probably more familiar with I. Right? There we go. Right? That's the sum of powers of 2. 1 plus 2 plus 4 plus ... 2 to the D. There's a name for this thing. It's a series, but what kind of a series is it? Is power a series? Maybe, but it's a summation, a series. It's a how does this grow? Does this grow arithmetically or does it grow geometrically? This is a geometric series. And there is a general form for this. If you have a different base B here, right? Then it's going to be B minus 1 over B to the D minus 1 or plus 1 minus 1, something like that. But our base here is 2, so the denominator goes away. And we're left with 2 to the D plus 1 minus 1. Kind of like Gauss's formula, this is going to show up over and over and over and over again. Why? If I gave you 3 bits to work with, 0, 1, zeros and ones, zeros and ones, right? What is the maximum value that you can represent? 2 to the number, so 3 minus 1, right? What if you were to sum up all the possible binary numbers? 0, 0, 1, 0, 1, 0. That's 1, 2, 3, 4, 5, 6, and 7. What would you get? 2 to the 4 minus 1. Right? Something like that, right? These are powers of these are not powers of 2, but these are the summations, right? Right? I think so. 1, 2, 3, 4, 5, 6, 7. All right, what is the sum there? So that's 6, 9, 13, 15, and 28. That can't be right. I did something wrong there. Is that right? 9, 6, 15. Okay, never mind. All right. Anyway, come back over here. Maybe I'm confusing myself. Anyway, this is a geometric series, and I'm pretty sure that this is correct. You could go ahead and fact check me on this, right? All right, so that means that we've got that many nodes, 2 to the d plus 1 minus 1, right? So in other words, all totaled here, we have n nodes in a full binary tree. And what is the depth here? What is the depth in terms of n here? In other words, I want to solve for d here. Take that 1 onto the other side, 2 to the d plus 1. How can I get rid of that 2? Log base 2 implicit on that side. And this is d plus 1. And then finally, what? Take that 1 onto the other side. D is going to be log of n plus 1 minus 1. Tell me, big O, characterization of that. Log n. Right? In other words, the depth is logarithmic, as long as it's full. The depth here is going to be log n. And if we can come up with operations that perform at most, they start at the root and then go down, right? At most, they're ever going to perform log n operations from the top to the bottom. If we can achieve that, we've achieved our goal. Unfortunately, spoiler alert here, you can have what are called skewed trees. A, B, C, dot, 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 down to Z. Let's go that. Right? Right. Everything has a right child. Nothing has a left child. Right? There we go. What do we call that? That's what? It's a linked list, all right? All you have to do is, how can I transform it? Nope. Power of AI, my ass. All right. Cut it, paste it, and then I can do there. There. It's just a regular old linked list. The depth there would end up being what? If there are n elements here, then the depth is exactly n minus 1. Right? In other words, order n. So there are trees out there that can screw us on the depth. Right? We're going to find out how to prevent that later on. Right? But the takeaway from this is that a full or nearly full binary search tree has a guarantee on its depth, right, where n is the number of nodes. Unfortunately, there are skewed trees where the depth is linear. Right? That is, d is going to be order n instead. Fortunately, it's not going to be n squared because we already said we're dealing with trees, right? That there's only going to be one path, and so we don't have this more complex arrangement of graphs or whatever, right? All right, 10 minutes left. Now let's go to Java. All right. So let's start an implementation of a tree, right? Of a binary tree, I should say. Okay, create a new package. And we'll go with UNL SOC trees. Right? All right, let's go ahead and create a binary tree. Binary tree. And I'm going to I learned from my mistakes before, I'm immediately going to parameterize this so that this binary tree can hold whatever data you want. Let me put that data in there, right? Private T piece of data, right? There. Well, there's not just one piece of data, right? Every node, every vertex in that tree has a piece of data, right? So I don't want just one piece of data. I'm going to want something else. I'm going to want a binary tree node that is parameterized. There's where I put my data, private T data, whatever you're going to do there. What else do I want in my binary tree node though here? Right, let's come back over here to an example. Here's a binary tree. Look at D. What does it have references to? A left child and a right child. Also, we might want a reference back to the parent because we learned our lesson with linked lists. Linked lists, you could just go one way unless it was a doubly linked list. Well, this is an undirected graph here. I want to be able to work up and I want to be able to work down. So let's put all three of those things in here. Private, binary tree node, T, parent. Let's use the nomenclature and terminology that we've just developed. Parent, left child, and right child. Data, we'll go ahead and put that first. There we go. There. There's our start on a binary tree node. Now let's come back over here to the binary tree. It doesn't just have one piece of data. What does it have? Okay, let's go ahead and go with a collection at first. Private list of what? Binary tree nodes? Node T? All the nodes. All right. Same thing with a linked list. Did we keep track of every single node? Nope. That took us back to a array. All right. So I'm not going to keep track of everything. What am I going to keep track of? The what? The head, and in this case, the head is called a root. All right. So that's called a root, and that's it. From the root, I can get anywhere else, just like a linked list. But it's going to be different this time because I could go left or I could go right, depending on the children that are there. So I'm going to have to come up with a clever way of keeping track. Have I already gone that way, or have I not? And I need to go that way, or what? Right. Also, might be helpful to keep track of a size. Right. Private int size. That is the number of nodes. Number of nodes. Right. I like size better. Size. It's private anyway, right? Etc. What does a default constructor here look like? Public binary tree. This dot root is equal to null. And what would the size be? Is 0. All right. Basic CRUD. I need a way to add stuff. Public void add element. Or I'll just say add element of X. Do I want an index here? Index? What does an index mean with respect to a tree? That doesn't even make sense, at least not yet. It will make sense later on. But no, I don't want you to just add it anywhere, right? I just want you to add it somehow, right? So I'm going to leave it just as add like that. Public T delete. T, actually, should I do this? Binary tree node T, all right, foo. All right, there we go. I want you to delete that binary tree node. That's called, what would we call those again? Leaky abstractions, right? Why would, no, what am I putting in this stuff? I'm putting in strings or integers or doubles. I don't know anything about binary tree nodes. Right? Why are you making me think about binary tree nodes? You're the binary tree, right? You should know what a binary tree node is, right? So delete element X. Right? Delete that string. Delete that whatever. Delete integer, whatever, right? And then let's go ahead and return null just so that it, compiles. Right? So there's create, delete. We also need retrieve and update. Right? So public T update T X, right? And we'll return null here just so that it compiles it as well. So what's left? Public T get element int index. Well, again, what the hell does index mean? I have no idea. Give me the element X. Does that make sense? It doesn't make sense at first. Why would you give me the element if I'm giving it to you to find? Right? But now we have to remember back to CS1. When we were doing searching and sorting, we were using comparators. When I want to search for a book by a particular author, I create a dummy value with the author set, but not with with no title, with no ISBN, with no rating, right? So I'm going to, this is going to end up being a dummy key here, dummy key. Right? I won't call it a dummy key. Instead, I'll just call it X. Find me a book by that author. Okay, here you go. Here's a book by the author. Right? And that's what I end up returning. I don't end up returning the dummy key. The dummy key is partial information. The thing that I end up returning is full information. So yeah, it does make sense from that perspective. And again, return null so that it compiles. All right. Now the problem here is, given this tree, how do I start searching? Let's get rid of all that. Right? I can only ever start at the root. If this were a linked list, right, then I only have one direction to go. Right? There's no guesswork there. But the thing that I'm searching for could be in the left subtree or it could be in the right subtree. How am I going to be systematic about this? How do I make sure that I explore the entire left subtree and then I go over here and I explore the entire right subtree because I'm trying to find J, right? We're going to need to be clever about that, right? And that's going to be tree traversal algorithms. I'm going to show you actually 4 of them. There's pre-order traversal, in-order traversal, post-order traversal, and breadth-first search traversal. And all 4 of them have their different applications, right? But that's where we'll continue it on Monday. Right? All right, any questions? No? All right, then have a good weekend.